Alors, c'est un grand plaisir pour moi de vous présenter le professeur Gafni de l'Université de Californie à Los Angeles. Alors, Gafni a fait son doctorat il y a quelques mois, quelques années, avec Berxikas au MIT. C'est quelqu'un qui vient des graphes, puis il s'est penché vers les algorithmes répartis, puis c'est une vedette dans la communauté pour plein de raisons. The floor is yours.
Okay, the floor is me for mimicking God and getting rewarded for it. This is a sort of a slight translation of the official title, which is Deus ex machina, which is hocus pocus. This is a joint work with Giuliano Losa. So what is this about? Where is the motivation? It's a question raised by Jayanti in 1994, which later we'll understand what's the question, and it's the question of robustness of deterministic objects. And when the question came out, there were two teams that proved that deterministic objects are robust. And looks like these two teams had a good intuition, but not really a proof. And one of these teams, I was on the team. And as they say, the buck stops here, and I'm to blame, not my co-authors. One of them is sitting here, Yehuda Afek. And it was not a proof. And why it was not a proof? Because I could not elaborate the idea behind the proof. And the moment that you cannot elaborate and say, what is really the idea? In my opinion, you don't have a proof. Okay, so it was a complex blah, 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 blah. And I thought it's probably right, but I couldn't make a convincing argument. So this is Erdos used to say, this is not that I had a Erdos, you know, it's the probabilistic people tell me, that Erdos has this notion, this is a proof from the book. There's a book in heaven, and, you know, when you have a good proof and it's clear, it's so this proof, I think, is from the book. And the cost of this proof was not, there is a Peter here, and I spent almost a year in 2007 trying to do this, and I spent the last 2 years with Giuliano Losa until the idea came up. And as usual, when you do good research, in my opinion, it's pretty disappointing because you see the idea and you say, why did it take 2 years? It's an idea of a week. Okay. So, context. In general, this kind of questions falls in distributed computing, in ancient distributed computing, not the blockchain now, the new. It falls in the area of computability. And essentially, in my opinion, the area of computability started with Fish, Lynch, and Patterson result that says in an asynchronous system, when one processor can fail, no consensus. And today it can be stated in a better way, initiated essentially by Wendwire and Santoro, and then pursued by Yehuda Afek and myself, of understanding that the difference between synchronous and asynchronous is false. There is no synchronous and asynchronous. There is synchronous, and there is a mobile failure, which is what we call today asynchronous, and there is a fixed failure, which is called synchronous. So if you take a synchronous network, and each round the adversary can take a processor and fail some of the messages that it sends, and each round everybody sends to everybody, then you cannot do consensus. Consensus is impossible. And impossible means no matter how much complexity, how much resources you spend on it. So this is about no complexity. Can you solve something or not? This is the first realization that when you have a model, a model has certain problems it can solve and a certain problem it cannot solve. So now, once FLP did this and FLP failed a single processor, we can talk about what if you fail 2 processors, and suddenly what if you fail 3? What did you fail? There is something that here Peter dealt a lot with called adversary, which is you fail this set or this set and stuff like this. So it's about failure. So you can ask, if you have number of processors and you have certain models and you associate with a model all the tasks the model can solve, then how does the world looks like? What are the types of these sets? And turns out today we know that if we just concentrate on, and Rachid has if we take, there is a model called failure detectors, which Rachid dealt with, we know about this quantization of the world of tasks. When we associate a model with all the tasks it can solve, that essentially these tasks can be characterized by set consensus. In other words, give me a model, replace it with set consensus and some delay and some waiting for some processors, and it can be solved. Okay, so this is one direction of taking this model and playing with the number of failures to get different models and asking what is the power. Okay, there is another context that we can take, which is the shared memory model. And as already explained by Yuda, shared memory model, a register is a state machine. State machine, you write, you get response, okay. If you do a read, you read the last write, okay. So we are talking about wait-free, that all processors might fail, but we know that the notion of fail in distributed computing is a bogus notion, because right now in the model that Yuda and I sort of generalized the model of Santoro and Wendmeyer, processors do not fail. It's the adversary that tampers with the communication. That and the processor is always alive, so we can ask at the end the processor, even if it's called fail, to output. So this notion of failure in the all distributed computing is a very confused notion and caused a lot of problems. Okay, so here is more example of state machines, fetch and add. Yuda already did the work for me. Total order, this is an interesting task, which is essentially the object, the state machine, returns the serialization of all the commands that were applied to it. So we know, for example, the total order can solve any task. If you give me the command, the state machine total order, and fetch and add, as Yuda said, it's a common 2, can solve only 2 processor, it's equivalent to 2 processor consensus. So, did I jump an example of state machine? Okay. So, the general question is, given n processor, communicating by sharing a set of objects, that we obtain a set of problems solvable, so we can think of processors and we give them to communicate this state machine, that state machine. There are many, many state machines. And now we say that we want to say, given n processors, how many, and we associate with each state machine the tasks that it allows to solve. How many different sets can be created? Okay, because we have supposedly, although we have only n processors, we can have many, many state machines. So do we get a lot of sets that can be... So that can be a lot of different sets that can be solved. And what's the current thinking that Yuda alluded to? That there is some rationality in the world, as in the same way that set consensus characterizes failures and failure detectors, also set consensus characterizes objects. Give me an object, give me these vectors that Yuda talked about of its set consensus power, and from now on, if you give me just the object of the consensus, or the set consensus power, and we have to show that there exists object like this, give me the object of the set consensus power, then I will solve this set. So there is therefore the number of vectors of n positions is finite. So we have a finite number of sets. Okay. So we have the problem of characterization. And the start of this, once everybody agrees that the proofs are not proofs, Peter and I started in 2007, we sort of asked the question, let's prove if we have an object that its power is n-1 consensus, meaning it can solve n-1 consensus, but in the old definition, it cannot solve, the object that use it cannot solve n consensus. And we ask, what is this set? Do all the objects of n-1 consensus power correspond in the context of n processors? They solve the same set of tasks. Thank you. And this is at the beginning. We just did a simulation. Rachid did a good observation, and he said, "But you actually prove that there is nothing as object goes. There is no object that is in between." For n processors, there is not object that it is in between n processors consensus, n-1 processor consensus, and n processors consensus. And this automatically leads that actually the set of tasks solvable in the context of n processors by n-1 power is the same set for all objects of n-1 power. Okay? So we see already partial characterization. But then came, this was motivated by the robustness question. What is a state machine? A state machine, you apply command and you get response. So if we have two state machines, we can think of it as a single state machine that we only enrich the set of commands. And the set of commands just will say, when I put this command, do I address this object or do I address another object? So when we say a register is a state machine, not only the register is a state machine, the whole memory is a single state machine. Only when you write here, you address this state machine, you write there, you address this state machine. So Jayanti asked a very natural question. And he asked, okay, we take an object and we know that it belongs to the realm, it solves the set of tasks that is solvable by n-1 consensus. We take another object and it solves the same set. Now I allow you to use the two. Now I give you a new object, and the new object is just a Cartesian product of these two objects. Can you now if you are dealing with something which makes mathematical sense, it should be that if you make a join of two things that by themselves do the same thing, when you take them together, they will do the same thing. Okay? But this question was very reasonable because at the time, there was a lot of models of you can address only a single object, the object can be non-deterministic, the object can be implemented standalone, you see, and turns out, as I'll say in the related work, there is a group of very smart people in Toronto that are expert at proving impossibility, and they showed if you take a non-deterministic object with a transition from state to state is non-deterministic, then robustness does not hold. So the only context that we assume that robustness is holding is in the realm that also characterizes n consensus power. And the realm that characterizes n consensus power is to take an object and use it in a program, in a finite program, okay? So using an object in a finite program is different than taking an object when you don't know ahead of time what is the program, and just providing a standalone implementation, that this implementation you can now plant in any program that you use. This is a very strong requirement of implementation. And what Peter and I addressed is, given we have an object that all we know is that if we plant it in a program, we cannot solve n consensus. We can solve n-1, but we cannot solve n. Can we implement this object in this program? We do not implement the object without knowing the environment it is used. Okay, so we just talk about deterministic object inside a program, used inside a program. And when we prove implementation, it's implementation inside the program. It doesn't mean that I know how to take this object and implement it, and then you can plug it in any. The context is very important. So what is the new thing? In other words, when you prove something, and a lot of smart people, especially Peter here, thought of it for a long time, you have to be able to pinpoint what is the new observation made. And I'll just pinpoint what is the new observation. And the new observation is, let's take all the n processors. And all the n processors simultaneously invoke the object. And now they all come with the results. So what we know now, what are the responses to all the objects? And we ask now, what is the state? Well, the state depends on how the object linearized the commands. But this is, what do we know? This is some secret that the object has in its belly. Okay, so the question is, if something exists that I do not have access to, does it exist? This is a philosophical question that once I compared it to the question of, if a tree falls in the forest, does it make a noise? If you were not there to observe it, and we cannot observe it. So all previous attempts were in the thinking, in the philosophical thinking, that the state exists. So there exists something. The departure here, no, it does not exist. So if it does not exist, what it is? Well, I have to invent God. When I don't know to answer, God is the answer. We know that ancient people did this. We are doing this too, okay? So there is God. And God is a helpful God. Actually, the whole model is an oracle, what we call oracle. We don't call an oracle God, but it's a God. And when you need, you say, see, I don't have the power of consensus, but I need result. So God, give me the result. God, if you ask for a result, God will give you the result. But what about the instances in which I can calculate what is the result? Sometimes I can calculate what is the result that God might give me. Okay? Then I'm talking about a good God. If a good God says, look, you actually, how did you get this result? I don't want to help you too much, but if you got this result the same way that I would have gotten it, then I will respond. If you want this result, yes, this is my response. So what is the meaning that you behave like God? God is not against you and not for you. God has knows what are the results like you. And when God goes now to answer what is the response to some new command, God will decide it non-deterministically. Of all the possible results it gives you, it will choose it non-deterministically. And there is a big difference between non-deterministic and probabilistically. I do not attach probability to any answer, but I say all answers are possible. Okay? So God says, if you will go through the process of showing me that you considered all results and somehow you choose this result, then I will respond to you. So the question is, how do we? The question is, I'm in a deterministic machine. I'm in a program. Everything in the program is deterministic. Where do I get non-determinism? And the answer is, after 2 years, asynchrony is non-determinism. Use asynchrony to choose the state. So what is the idea? We have something which is called epsilon agreement. Epsilon agreement is one processor says A, the other processor says 0, and the other processor says 1, and now they argue, and they end up epsilon from each other. Okay, this process is completely non-deterministic. It depends on speed of processors. Okay, so if I will take this epsilon agreement and now divide the line into states, I can, depending on timing, on asynchrony, I can end up in any interval. The only difference is that I cannot solve consensus. I can end up on the border between intervals. But I want to use this in the context of, in our context, we have two objects. And this is a result. At the time, we didn't understand that this is quite the same as BG simulation, the BG, that if you have two independent consensuses for two processors, one of them, they can solve the consensus. So if you are between states, you get consensus on what will be the step for the other object. If you end up interior to a state, you get consensus for what will be the state. But if you know the state, Peter and I already did simulation if we know the state, so the whole thing is solvable. So this is in a nutshell what is the, and now you have to prove that you invented now a new model of object. And you have to show that previously we have the definition of Maurice Hirley, what is n-1 consensus power. You have to show me that now the same specification, if it's run by God, have the same consensus power as previously. You cannot as a user, you cannot use God to extract some more synchronization power. And this is really easy to prove because you really imitated God. The only thing is, how do you know that you don't cheated God? Well, you are working in a program. So we can see in the program whether you are cheating or not. So God can see and will not reply to you. And that's the whole idea. Well, related work, Hirley formulated the problem. Peter and I worked on it, and this is the basis of all that was done here. A lot of work. We spent on it a year almost. Niger and Peterson, they proved with us a And the Toronto people proved that anything that I know, essentially now with Tueg and a student, David, they proved that any variation of what we are asking doesn't make mathematical sense. But we claim this makes mathematical sense. So also, the idea that there is no real state of an object come naturally in the context of implementation of object. So this was already considered by Hurley and Wing. When they did implementation, they ran into some problem of linearizability, and they said, okay, the state of the object is not a state, it's now a cloud of states. So this is something that comes very naturally in the context of implementing, because you know, it's up to you, so you define. In the context of thinking of a machine, that's why I call it, our thinking was of a real machine that you go to it and the machine does the linearization, which is a little bit now today, to me, sounds, in retrospect, sounds very bizarre. The more natural thing is to think of a cloud. And this is what we think. So the only challenge, in my opinion, so we know that with respect to consensus, it is robust. But now suddenly we introduce set consensus. We didn't solve that with respect to set consensus, it's robust. So, but the more interesting question in my mind is that we are talking about implementation of an object. The whole notion of consensus power is inside a finite program. But we like to be in the realm of what Yehuda talked about, taking an object and not knowing in what context you are going to put it and say, this is its power. We don't know how to do that yet. And I'm 2 minutes too late.